Hey guys, in this video, I'm going to do the 4 combination sum problems on LeetCode. Now, what's interesting about these problems is that they're really similar in the way they can be coded. So once you understand how to do the first one, the other 3 problems are just slight changes from that. So let's dive right in. This problem tells you to find all the combinations of numbers in a given list of numbers that add up to some target number, and you are allowed to reuse the same number. Before I start coding, I'm going to head to the drawing board to get a conceptual understanding of this problem. We can find this by making a function that iterates through all the candidates, and I'll just call this function f for simplicity's sake. For each candidate, the target number would be subtracted by the candidate to get the remaining target quantity. At the same time, we need to keep track of which numbers the recursion traversed through the tree of possibilities. So I'm going to add a parameter called cur_path to store this current path of candidates traversed. And I'm going to initialize this to an empty list since we haven't traversed anything just yet. So now let's start actually traversing. From the root function, we iterate through all the candidates, producing the recursive function calls. We can do this with a for loop. So you can see that for the first recursive call, the remaining target is 7 minus the 0th indexed number, which is 2. And it's the same process with the rest of the candidates. So if these are the candidates, you see it's 2, 3, 6, 7. Right, so it's 7 minus each of these numbers. And this is all being done with a for loop. Additionally, we append the candidate to the current solution list to keep track of what we have just seen. Right, so for this call, we've just seen 2, so we have to append 2, 3, 6, and 7. So note that the recursive call for the last candidate, 7, the remaining target is now 0. And this means that we've actually found a valid solution. But we'll come back to that later. But for now, I want to shift our attention to the recursive call for candidate 2. Just so we have a more elaborate example to show what's going on. So what happens after calling f of 7 minus 2 with the current solution list containing 2 recursively? Well, 7 minus 2 is 5. So now we have f of 5. But this call also runs a for loop going through all the candidates. So now we have the following recursive calls. 5 minus 2, 5 minus 3, 5 minus 6, 5 minus 7, as well as the candidates for each call appended. Note that the calls for 5 minus 6 and 5 minus 7 result in a call of the function with a negative remaining target. We need to stop the recursion at this point along the path by just returning. This is one of the base cases we need to take into account when we code this. I've written some more recursive calls to just illustrate another case where the remaining target is 0. And you can see that we found another combination, 2, 2, 3, totaling up to 7, which is equal to the initial target of 7. And this case, just like up here, where we also found another 0 remaining target, that's another of the one of the base cases we need to take into account. Okay, so now I think we know enough to code our solution. So I'm gonna write current solution. This is our array for current solutions that are used in the recursive calls. And this array will store all valid solutions. And then here, so I'm going to call the recursive function build solution. Candidates, target, current solution, and solutions. And then we need to return all valid solutions. So let's write out build solution. So our base case is if the we're subtracting the target by the candidates recursively, right? So if the target, and what we're really saying here by now is the remaining target, if the remaining target drops below 0, then just break out of the recursion. If the target is 0, then we can sort the current solution in case if we are getting the numbers out of order. And then if the current solution is in if it's not in solutions, then add it. And then end it, break out of the recursion. So now our recursive call is we're going to iterate through each candidate and then call build solution on them. Right. We subtract the target by the current candidate. And then we create an array with the current candidate added to the current solution array. And just pass in the solutions. And let's try it out. Self. Oh. Yeah. That call doesn't need self. Okay, that's my bad. So the preliminary test cases are all accepted, and let's submit. And it is accepted. And so that does it for combination sum 1. Keeping in mind what we did for combination sum 1, let's head over to combination sum 2. The process for combination sum 2 is similar to that of combination sum 1, except that we'll need a way to not solve the solution for the same index in our for loop, because that will lead to combinations with duplicated numbers, which is what we don't want. Let's start with the example given in the question. So here are the given candidates with the target 8. Like back in combination sum 1, for each of the candidates, we'll need to subtract the target by that number and keep track of which numbers were subtracted. But the difference here is that we need to make sure we're not subtracting the same number more than once in any path along the tree of possible chosen numbers. To do this, we need to make sure that the recursive call is performed on the next index forward in the list of candidates and not on the same index more than once. Therefore, the parameters that the recursive function needs to contain here is remaining target, the current solution array, and if you remember, these two parameters are just like back in combo sum 1. And now this is what's different. So the difference here is that I'm going to add a variable that represents the index of the next candidate in the candidate array. Not sure why it's doing that. This way we can begin the for loop at the next index instead of at the same index in the candidate array. So now let's walk through the recursion. So what's important here is that we pre-sort the candidates. This way, it's easy to detect if the next number is the same as the number that you were just on, like in this case here. So from the root of the recursion, we're starting with the range of 0 to 6. I just wrote the first 2 calls of the for loop because it already shows what we need to see, and writing the whole thing out would just take forever. So for I equals 0, we have f of target minus the number at the 0th index, which is 1. So we have 8 minus 1. And we put 1 in the current solution array. And then the next recursion should start at I plus 1. Remember, I is 0. So 0 plus 1 is 1. So the next recursion should start at 1 along the path of this call. For I equals 1, we have f of 8 minus 1. Add the I in the current solution array for this function call, and then increment the index for the next recursion. So if I equals 1, then the next recursion should start at 1 plus 1, which is 2. Let's hold off on that thought and just go back to the case where I equals 0. More precisely, it's recursive call here. Let's look at the recursion actually being done here. So our remaining target is now 7 with 1 already in the current path array, beginning at index of 1. This means our for loop for this recursive call is from range 1 to 6. For I equals 1, our recursive function is f of 7 minus 1 with a current solution of 1, 1, right? Because this 1 gets appended to this list. And then the next index, 1 plus 1 is 2. And you can see how I'm just following the same process with all the other recursive calls. So let's write out the code to do this. So the test cases are accepted and submit. While this is technically a correct solution, it's not really optimized. That's why we're getting a TLE. So in here, across these two branches of recursive calls for I equals 0 and I equals 1, notice that the same exact call is being called more than once here. So for the case where I equals 1, we actually see these two same calls being done as these two. That's a lot of wasted computational effort. So this means that we can actually revise our code and add some logic in there to prevent this from happening. Okay, so I've copied and pasted the test case to here, case 4. It's the candidates and the target. So again, let's run this just to let's see if we can get the same. I think we should. Yeah, we still should get time limit exceeded. All right. So why are we getting that? Now it's because we're actually solving some of the same problems. So we need some kind of optimization here to prevent that. And one thing we can do is right here. We can add a condition where build solution only gets recursively called when at the start index, because you are already incrementing the index for this for loop by 1. If I equals start index, right? Because if you're running, if the for loop is at start index, then you run this function recursively for the next index. And the other case is if the value at the previous index is not the same as the value at your current index. Now it's time to run our code. So now this case is accepted. And let's submit again. Yeah, so it's accepted. So that does it for combination sum 2. With the second combination sum problem tackled, let's head on over to the third one. So combination sum 3 is actually quite similar to combination sum 2, in that instead of iterating through a list of candidates, you're iterating through what could be a list of numbers 1 to k. So it's as if you just had like a list of candidates. And we I for I in range 1 through k plus 1, right? So it's as if we were just solving the previous problems with the candidates array of this. But we don't actually need this. So because if we know that k can only take on values from 1 up to k, then all we need to do is when we call the recursive function, we decrement k by 1. Since each number is used as at most once, that's one of the requirements, we can still use the start index method that we were using back in combination sum 2. Right. So same lists for solutions, storing all the valid solutions and current solution. We use a start index of 1 because only numbers 1 through 9 are used, right? We can't start with 0 because that'll violate this requirement. Alright, so we call this So in this version of build solution, n is equivalent to the target we're trying to find. So just like the previous problems, if the target drops below 0, then just break out of the recursion. And now for the base case for a good solution. So if the target equals to 0 and we've reached the end of k, the max k, but in this case we're going backwards, which will give us the same result. So if k is also 0, sort it, and then if cur solution not in solutions dot append cur solution, right? Notice that this part here is exactly the same as the previous problem. Well, just without the sort, but it's exactly the same as back in combination sum 1. And now for the recursive call. So for I in range. Now, remember when we said start index starts at 1? So we start in range start index up to 10, exclusive. So now the numbers 1 through 9 are all covered. We decrement k by 1, and then decrement the target by the candidate, which is I. Sorry, I hit the wrong key. And at the same time, we append I to the current solution, just pass in solutions, and then just like back in combination sum 2, we increment the index I in preparation for the next recursion. So let's run it. Okay. Accepted. And let's submit and see if it passes. All right, and it's accepted. That was combination sum 3. let's move to combination sum 4. In combination sum 4, we're asked to find the number of possible combinations that add up to a target given an array of numbers. So in this case, we're not actually being told to find the actual combinations, but the number of possible combinations. So again, this is really similar to combination sum 1, where we are finding the actual combinations, but we just need to rewrite this code in a way where we are counting the number of solutions rather than keeping the solutions themselves. It's also similar to combination sum 1 in that you can see that we're actually allowed to repeat numbers. To do this, well, I'm gonna just copy this. Let's ignore that function, this top level function first. Okay, what do we need to change in order to count the number of solutions rather than keeping the solutions themselves? All right, so now instead of candidates, we have nums. We have target, but we don't need current solution because, again, we're not keeping track of the actual numbers. We're counting the number of solutions. We're also not keeping track of the total number of solutions for a similar reason. So let's go through each of these and modify them. So if target is less than 0, that means we have not found a valid solution. So instead of just breaking out of the recursion and returning nothing, we return 0. Now, we know that if the remaining target in a path of recursions is 0, we have found a valid solution. Therefore, instead of keeping track of the solutions, we just return 1 because we found one valid solution. And in this case, the candidates is actually called nums. Right? So nums, passing in nums, and then target, which we passed in, minus the number in the nums index, nums array. And again, we don't need these two anymore. In the main function, we just call build solution. Yeah, just return that. None type is not a valid value. Okay. Okay, so this is what I was missing. So we need a variable, which I call numCombos 0. We need a variable to just count the number of combinations for the recursive calls. Okay, so these two cases are accepted, and let's submit. Okay, so we're getting time limit exceeded. Let's see if there's some kind of optimization that we can perform on this current solution. Now, the first thing that comes to mind here is, since this build solution function follows a very similar pattern to some other problems, to some other recursive problems. It's almost like the way that memoized Fibonacci is done. We can just implement the same type of memoization. Our memo will be a map. I'm just going to pass it in, memo, and before the recursive calls that are done by the for loop, I'm just going to say if target, right, in memo.keys, then return memo target. Otherwise, we proceed with the recursion, and before the return, I'm going to store the number of combinations for a given target in memo. Okay, now let's hit run. Oh, I'm missing the memo here. Okay, so both are accepted, and now let's hit submit. And it's accepted. Cool. All right, so that was combination sum 4. And now we've done all 4 combination sum problems. Hey everyone, so that was it. All 4 combination sum problems on LeetCode. Hope you enjoyed the video. And so one more word about the space and time complexity of these problems. I'm actually not sure what the space and time complexity is for these problems. So if you have a good idea of what this is, please chime in the comments, and I would be happy to hear. You probably help out a lot of people too. So that does it for this video. Hope you enjoy it. See you in the next one.